Okay, so let's start. Hi, welcome to week 11's problem solving session. And what we'll do today is we'll first solve some problems from week 11's assignment, and then we'll solve some problems related to week 12's content. So let's start. So the first question that we'll look at is the following. Select the correct option. The options are Elgamal encryption scheme does not have the malleability property. Uh, Malleability just means that you can modify, given a ciphertext, we can modify it to create a ciphertext for a new message. Option B is the hardness of CDH or computational Diffie-Hellman may not be the same as the hardness of DDH or decisional Diffie-Hellman. Option C is gap CDH. Assumption says that computing g to the xy given g to the x and g to the y is not possible in the presence of a DDH oracle. And option D is there exists some public key encryption scheme that is malleable and CCA secure. So these are just the questions from the assignment. So if you know the answer and would you like to answer, you can answer in the chat. Okay, so let's go over all the options. The first option is that the Alkemal encryption scheme does not have a malleability property. Well, this is false because suppose yeah, it has malleability properties. Let's see why. So suppose C1 comma C2 is the encryption of M. Then C1 is equal to G2 rho beta for some beta fit uniformly at random from ZQ. Here I'm assuming that the cyclic group has order Q. And uh, C2 is equals to M times Y, or rather the public key to the beta. And the public key would be G to the alpha. So this is M times G to the alpha beta. Now suppose we a ciphertext for gamma times M for some gamma of our choice. This is C1 comma C2 prime, where C2 prime is just gamma times C2, which would be gamma times M times G to the alpha. It's easy to see that this is a valid C1 comma C2 prime is a valid ciphertext for gamma times M, and so algebra encryption scheme is malleable, so A is false. What about option B? Option B is the hardness of CDH may not be the same as the hardness of DDH. Well, that is true because we in fact know of some groups in which CDH is believed to be difficult, but DDH is believed to be easy. DDH is known to be easy. So B is true. What about C? Gap CDH assumption says that computing G to the X given G to the X and G to the Y is not possible in the presence of a DDH oracle. Well, gap CDH assumption just says that solving a CDH problem is difficult even in the presence of a DDH oracle. And what is the CDH problem? The CDH problem is just the problem of computing G to the X, Y given G to the X and G to the Y. So yeah, option C is also true. What about option D? There exists some public key encryption scheme that is malleable and CCA secure. Okay, so if a scheme is malleable, right, D is incorrect, yes. So if a scheme is malleable, then uh, given the challenge hypertext C, we would be able to manipulate it and create a new hypertext C prime, which is valid. So that hypertext, when we ask a decryption oracle query for that ciphertext, we will get we will get a valid message as a response, and using that we can use that to break the security of the encryption scheme. So yeah, there does not exist a malleable encryption scheme, just CCA secure. So D is false. So only B and C are true. So now let's look at the next problem. The next problem is identify the correct options. Option A is identification scheme in the public key setting consists of three algorithms. Option B is in a three-round identification scheme, the prover's commitment and response are received by the verifier. In the no message attack, just the public key is not enough to generate a forgery. And option D is an arbitrary forging attack, which requires the honest party to sign random messages, is only possible in theory and it's not practical. Okay, so which of these are correct? Oh, so yeah, I got incorrect. Okay, yeah, okay. Okay, so let's go over all the options. Okay, so option A is identification scheme in the public key setting consists of three algorithms. Well, it doesn't. It consists of four algorithms. And the algorithms are the key generation algorithm, the algorithm P1 that the prover uses to commit to the verifier, that is, the prover uses to generate I. Uh, then, once the prover gets a random challenge R from the verifier, the prover uses another algorithm P2 uh, to generate a response S. So that's three algorithms. And finally, there is this algorithm that the verifier uses to verify that the so uh, to verify that the prover has responded to its challenge correctly. That is, it uses an algorithm to check that uh, on input I, R, and S, you get output one, you get accept. So the public key setting identification scheme does not use three algorithms; it uses four algorithms. Is this fine? Okay. So option B is in a oh, no, yeah, over here the prover algorithm is split into two different algorithms, P1 and P2. Because if you remember in the commitment scheme, the prover was just committing once and then it was just opening, right? Over here, the prover sends two messages. So yeah, it uses two algorithms. Option B is in a three-round identification scheme, the prover's commitment and response are received by the verifier. Well, yeah, this is true because this is just how a three-round commitment scheme works. The prover first sends the commitment, then the verifier sends a random challenge, and the prover is supposed to answer, like reply to this random challenge and convince the verifier that, yeah, everything's fine. So, yeah, B is true. Option C is in the no message attack, just the public key is not enough to generate a forgery. Well, this is false because this is exactly what happens in a no message attack. You just use the public key to generate a forgery without even having to like query the signing oracle at all. So yeah, C is false. And in fact, we also saw an example of a no message attack in class. That was an attack on the RS on the vanilla or the plain RSA signing scheme, and the attack was as the following: to like we have the public key E, so we just yeah output anything, that was just the attack. So yeah, like there are signature schemes against which we can make like we can have no message attacks. So C is false. And what about option D? An arbitrary forging attack, which requires the honest party to sign random messages, is only possible in theory and it's not practical. Well, this is also false. And here's one situation in which you can like force your adversary, you can force the verifier to sign, verifier or the honest party to sign random messages. Okay, consider this situation. Let's say you are sending some messages. Let's say there are two parties, A and B, and what A does is A sends messages to another party C, and A knows for a fact that B is intercepting these messages and try to decrypt them. Now, suppose that B has divided this this interception and decryption process into two parts. Let's say they have an intercept session. They have an interception station near A's home, and they also have a cryptanalysis section somewhere else. And what the interception section does is that it intercepts messages and sends these messages to the cryptographic section. But to convince the cryptographic section that these messages or these intercepts are coming from the intercept section, the intercept section just signs every ciphertext that it sends. Okay. Now, what A can do is A knows this is happening, so A can just send random ciphertexts. The intercept station would sign these ciphertexts and forward it to the cryptanalysis section, and A can just intercept this communication. And in this way, uh, A would now be able to force its adversary B to sign random messages. So such attacks are possible in practice. Yeah, and this is like something. This is somewhat similar. So the motivation of this definition of uh, signature keys which are secure even against such attacks, where you are able to get random, where you're able to get the honest party to send to sign random messages. The motivation for such attacks is very similar to the motivation for studying CCS security in the for encryption, right? Because such attacks uh, in which active adversaries can make honest parties do their bidding are possible in practice. So D is also false. Is this fine? Okay, so now let's look at the third problem. The third problem is the following. Consider the following security experiment against the textbook RSA signature. The PPT adversary is given the public verification key VK and a message M by the verifier. The challenge for the adversary is to come up with a valid signature for M without Oracle access to the signing oracle. That is, without even asking one query to the signing oracle. And the options are: if the RSA assumption holds, the adversary can only win the experiment with negligible probability. Option B is, even if the RSA assumption holds, the adversary can win the experiment with non-negligible probability. Option C is, if the RSA assumption does not hold, then the adversary can win with probability 1. And option D is, the success probability of the adversary cannot be related to the RSA assumption. So which of these four is correct? Yeah, it's D. Okay, let's see why. So here's the RSA assumption. Given N, comma E, comma X to the E mod n, for random x, for a random x in the group, finding an EH root of x is R. So this is the RSA assumption. And the key thing over here is random x in G. Now, the thing is, given m may not be x to the mod n for a random x. Yeah, so the RSA assumption only talks about the average case hardness and not the worst case hardness. And it is possible that the message that the verifier sent to the adversary might not be x to the, its distribution might not be the same as the distribution of x to the e mod n where x is random. So yeah, uh, so basically what's happening is in the security experiment, we want the worst case hardness of finding the eth root mod n, but RSS assumption only talks about the average case hardness of that problem. So we cannot reduce uh, the question of with what probability this adversary would succeed to the RSA assumption. Is this fine? Okay, so let's move to the next problem. The next problem is which of the following is or are correct? The options are any identification scheme can be used to get a signature scheme. Option B is any encryption scheme cannot be used to get an identification scheme. Option C is public key identification schemes provide security even against malicious adversary. And option D is CCA secure hybrid ciphers based on the Diffie-Hellman problems require only the DDH assumption to be true. So which of these are true? Okay, so it's you are saying A and C are true. So let's go over the options. Option A is any identification scheme can be used to get a signature scheme. Well, this is true because they can just use the Fiat-Shamir heuristic to convert any identification scheme to a signature scheme. Okay, you are saying asking if D is also correct. Okay, D is not correct, but we'll talk about it when we get to D. So okay, yeah, A is correct because of the Fiat-Shamir heuristic. Now let's look at B. Any encryption scheme cannot be used to get an identification scheme. Well, this is true because if your encryption scheme is a private key encryption scheme, then using that you cannot get an identification scheme. Because yeah, the two live in completely different worlds. One in the public, the encryption scheme lives in the private key setting, and the identification scheme lives in the public key world. Yeah. So B is also true. What about C? Public key identification schemes provide security against malicious adversaries too. Well, this is true because like you can have CCA secure public key identification schemes and they will work against active or malicious adversaries as well. And what about option D? CCA secure hybrid ciphers based on Diffie-Hellman problems require only the DDH assumption to be true. Well, this is false because as we saw in the class, in fact, when your attack model is when your security model is CCA security, an adversary in fact gets an oracle access to the DDH solver. Yeah, option B has not over here. Yeah, yeah. So as I was saying, while if your security model is the CCA security, then your adversary actually gets an oracle access to the PDH solver. So even if like DDH assumption holds, it's not exactly useful because the adversary can still somehow solve the DDH assumption, the DDH problem using this Oracle access. So in fact, what we require for CCS security, secure hybrid ciphers based on Diffie-Hellman problems, is the gap CDH assumption, which is basically saying that you cannot solve the CDH problem even in the presence of a DDH oracle. So D is false. We need something more than the DDH assumption. We need the gap CDH assumption. Is this fine? Okay, so let's move on to the next problem. The next problem is we want to build a variant of OTP or one-time pad based on multiplication modulo a prime number P, where the message space, the key space, and the ciphertext space are all the same. And the encryption of a message M is defined as M times K mod P, where M is the message, K is the key. And the decryption of C is C times K inverse mod P, where K inverse is the multiplicative inverse of K modulo P. Select the correct option or options. Option A is the scheme is not perfectly secure when the key space is ZP. Option B is the scheme is not perfectly secure when the key space is ZP prime, ZP cross. Option C is the scheme is not perfectly secure when the key space is ZP and nor is it perfectly secure when the key space is ZP cross and none of the above. So which of these are correct? Yeah, okay, so A is correct and uh, here's why. So what we'll show is that A is correct and B is false. So uh, that means that C is also false. And yeah, D can't hold because it's none of the above. So what we'll show is that A is true and B is false. Yeah. Okay, so let's see why A is true. Yeah, so in this case, the encryption scheme is does not even satisfy the correctness property. Yeah, okay. Yeah, I mean, yes, I agree. Some options are confusing. Also, like sometimes the question asks you to identify the correct options. Sometimes it asks you to identify the incorrect options. So that can also get confusing. Yeah, I totally agree with you on that. Yeah. So in case of in case when the key space is ZP, I claim that the correctness property is not true. So forget about perfect security. The like encryption scheme is not even properly defined. Here's why. So if okay, so the correctness property is not true. Uh, that is, there exists message comma key such that the decryption with respect to key of encryption is not equal to let okay consider k is equal to 0 and m is anything in ZP. Yeah, so k, m, and c are all the same. So if k is ZP, m is also ZP. So consider k is 0 and m is ZP, right? Now, uh, the C defined as encryption is equal to m times 0 mod is equal to 0. And decryption of this is equal to C times K inverse mod P. However, 0 is not in ZP cross and does not have a multiplicative inverse. Modulo P. So this thing is not well defined. So in this case, we can't even decrypt some messages correctly when the key is 0, right? So forget about perfect security. This scheme is not even a valid encryption scheme because it does not even satisfy a correctness. So A is true. So that immediately implies that C and D are false because A is true. So none of the above can't be true, and the scheme is not perfectly okay. Wait, to show that C is false, we need to show that B is true, right? Yeah. Okay. So A is true implies B is false. So now let's see why B is true, and that would imply that C is false. So we need to show that the scheme is perfectly secure. That is, okay, so what we'll do is we'll do this. For any distribution on the message space, any C in the ciphertext space, M1, M2 in the message space, the probability that ciphertext is equal to C given message is equal to M1 is the same as and if you recall, this was an alternative and equivalent definition of perfect security. So this definition basically says that the ciphertext is independent of the underlying message. So if I give you the ciphertext, you shouldn't be able to. If I give you the ciphertext, you get no information about the underlying message. So let's see why this is true. So probability that C is equal to C given M is equal to M1. So what is this? This is the probability that the key K, or rather C is equal to M times K mod M, or mod P. Right. Now since M is in ZP cross, this is equal to M is in ZP cross. So recall that in option B, K is ZP cross, but K and MC are all the same. So that means that M is also in ZP cross and therefore its inverse exists. So we get this. Now, so the probability that, oh, I should write M1. Now, we pick the key in the OTP, we pick the key uniformly at random, right? So the probability that K is going to be this particular number, C times M1 inverse mod P, is 1 over the size of its domain is equal to 1 over size of ZP cross is equal to 1 over P minus 1. Let me add a page. Similarly, is equal to the probability that C is equal to M2 times K mod P, which is the same as probability K is equal to C times M2 inverse mod P. Again, M2 inverse exists as M2 in ZP cross. And again, this is just 1 over P minus 1. So regardless of the distribution of the distribution on the message space, and regardless of C and M1, M2, these two probabilities are the same. And so when K is at P cross, the scheme is perfectly secure. So option B is false. And what does option C say? The scheme is not perfectly secure when K is at P. That is true. Nor when K equals to ZP cross. That is false because we saw that when K is at P cross, the scheme is perfectly secure. So yeah, C is false. Actually, P is false. Yeah, so the only correct option is A. Is this fine? Okay, so let's look at the next problem. Okay, so the next problem is about the Schnorr identification scheme. The problem is as follows. Suppose that there exists a PPT algorithm that can generate two valid transcripts I, R, S and I, R prime, S prime. So over here the commitment I is same in both cases. However, R prime is not equals to R and S prime is not equals to S. So suppose there exists a PPT algorithm that can generate such these two valid or accepting transcripts for Schnorr's identification scheme. And the question is, what can we say about the D-log assumption? That is, does the D-log assumption hold or does the D-log assumption not hold? Okay, would you like to take a guess? Okay, so actually the answer is it does not hold. Yeah, so what will, okay, yeah. So what we'll do is we'll do the following. Suppose you have an algorithm A prime that can generate two such transcripts. Okay, we will use that to break the D, to compute the D-log of some number, to compute a D-log. Okay, so let's look at the D-log game. You have a verifier, you have a D-log adversary, and you have an adversary for this, which can generate two transcripts. Okay, now what does the DLog verifier do? It picks X uniformly at random from ZQ. So I'm assuming that the group has order G. And sorry, the group has order Q. The group G has order Q. And it sends Y equals to G to the X to A. And A just forwards this to A prime. And A prime is supposed to generate two transcripts for this Y. So what does it do? A prime generates I, R, S and I, R prime, S prime such that okay, both of these are transcripts are valid. So both of these should satisfy the the equation of the verification algorithm of Schnorr's identification scheme, right? And what happens in the verification of Schnorr's identification scheme? Well, it's the following, right? So in the verification process of the Schnorr's identification scheme, it is checked that, okay, first of all, I is G to the B for P which is random from ZQ and uh, G to the S is equal to G to the B times, uh, okay, but instead of writing G says G to the B, let me write this as I times uh, G to the, okay, I times Y to the R and G to the S prime is equal to I times Y to the R prime. Now let us see what these two give us. So G to the S equals to I times Y to the R. G to the S equals to I is G to the B and Y is G to the X. So Y to the R is G to the XR. So this implies G to the S equals to, rather let me write this. G to the B equals to G to the S times G to the minus XR. G to the B equals to G to the S minus XR. And this implies that B is equal to S minus XR mod Q. Similarly, G to the S prime is equal to I times Y to the R prime is equivalent to G to the XR prime. This is equivalent to G to the B prime is equal to G to the S prime times G to the minus Rx prime G to the B. Oh wait. Oh, there is no B prime. There is, yeah, I is the same. So it's just B. So this is G to the B is equal to G to the S prime minus XR prime, which implies B is equal to S prime minus XR prime mod Q. So therefore, let me call this one two. So comparing these two, we get that S minus XR is equal to S prime minus XR prime mod Q, which implies X is equal to S minus S prime times R prime minus R inverse mod Q. Okay, so this is what X is. And what our adversary A does is A knows okay, so A prime sends these two transcripts to A. Now A knows R, A knows S, A knows R prime, A knows S prime, and A knows Q. So A can compute this. It sets X to be, or rather X prime to be, uh, what was it? S minus S prime. And then just send X prime to the. Now, so X prime equals to X, i.e. success probability of A prime is the same as, sorry, success probability of A is the same as the success probability of A prime, which by assumption is non-negligible. Over here, I'm using Q because the size of the group is Q. Okay, so wait, so this should be like log Q, yeah. And so over here, our security parameter would be like, wait, yeah, the security parameter would be N, and that Q would depend on N, right? So the success probability of A is the same as the success probability of A prime, which we have assumed is non-negligible. So A does succeed in finding the discrete log with non-negligible probability. The question is A efficient? Well, if A prime is efficient, then A gets this in polynomial time or probabilistic polynomial time. And once it gets this, it can easily compute, it knows Q, so it can easily compute R prime minus R inverse mod Q and multiply that with S minus S prime and again like do this entire multiplication mod Q, right? So if A prime is efficient, then A can find out X prime efficiently, right? Now recall that we have assumed that A prime is PPT. So A is PPT because A prime is PPT. So A is an efficient adversary for the discrete log problem. So the discrete log assumption does not work. Is this fine? Oh, can you hear my voice clearly now? Like, also, if you, in case you missed something, do you want me to go over something again? Yeah. So, do you want me to go over some part again? So you can if you missed something, you can tell me from where you missed, and I can repeat that part. Oh, oh, so okay, there is no hybrid over here. Okay, so okay, so did you miss from here? Okay, yeah. So should I repeat? Okay, so are these two fine? One and two? Okay, I don't exactly understand what's what second one last. Okay, so let me go once again. So yeah, we have that g to the s equals to I times y to the r. And if you solve, like, if you basically put in the values of I and y over here, you would get that b equals to s minus xr mod q. So similarly, you would get that B equals to S prime minus X R prime mod Q. So if we compare these two, we get that S minus XR is equal to S prime minus XR prime mod Q, right? Now I can move S prime over here and this over here. So what I get is S minus S prime equals to R minus R prime times X mod Q. Oh, this is wrong. This should be R minus R prime. Sorry. So this is R minus R prime. Yeah. So when we move this S prime to here and RO to here, we get that X equals to S minus S prime times R minus R prime inverse mod Q. So now once A gets these two from A prime, all it does it computes S minus S prime times R minus R prime inverse mod Q. Why can it do this? Well, it knows R prime and Q. So it can compute R minus R prime inverse mod Q efficiently. It also knows S minus S prime. Sorry, it also knows S and S prime. So it can compute S minus S prime and multiply R minus R prime mod Q to it and then again go mod Q. So because of that reason, this X prime is exactly equals to X. So A can compute a discrete log efficiently as long as A prime is efficient, right? The thing is, A prime is efficient. That was our assumption because the question says that there exists a PPT algorithm that can generate two transcripts. So A prime is efficient and therefore A is efficient. So is this fine? Yeah. Okay. So these are all the questions that are from week 11's content. So now let's move on to questions from week 12's content. And the first question from week 12 is select the correct option for the Fiat-Shamir heuristic. The first option is it can be used to convert any identification scheme into a signature scheme. Option B is we can prove the security of there's a typo here. We can prove the security of the yeah, sorry, the typo. Yeah, so option B is we can prove the security of the resultant signature scheme in the standard model. Option C is we can prove the security of the resulting signature scheme in the random oracle model or ROM. And option D is none of the above. So which of these are correct? Okay, so let's go on the options. Option A is it can be used to convert any identification scheme into a signature scheme. Well, this is true. So A is option B is we can prove the security. Yeah, B, C is true, right. So we can prove the security of the resulting signature scheme in the standard model. This is not true. We saw that we can prove the security of the resulting signature scheme if the hash function used by the Fiat-Shamir transformation is modeled as a random oracle. That is, option C is correct. We can prove the security of the resulting signature scheme in the random oracle model. Yeah, so C is correct, P is not. At least till date, we don't know how to prove the security of the resulting signature scheme in the standard model. And option D can't be true because A and C are true. Yeah, so the correct answers are A and C. So now let's look at the next problem. The next problem is for the Shamir Shikrit sharing scheme, which of these options are correct? The correctness holds if Lagrange interpolation is performed over a ring. Option B is the correctness holds if Lagrange interpolation is performed over integers. Option C is the privacy does not hold if the secret is said to be any term other than the constant term. And option D is none of the above. So which of these options are correct? Okay, so let's look at all the options. Option A is the correctness holds if Lagrange interpolation is performed over a ring. So you are saying that B is true. In fact, both A, in fact, okay, A is false and B is also false. So let's see why. Okay, I don't have any space. Let me just move this little up. Yeah. Okay, so A is false. So A is false because so the correctness sharing relies on the fact that uh, a degree D polynomial over a field has at most three roots in the field. However, this is not true over rings. That is, over rings, it is possible to have a degree D polynomial which has more than D roots. So yeah, the correctness need not hold over when we perform Lagrange interpolation over a ring, because what can happen is you can have, even if you have D plus one many poly points, there might still be multiple degree D polynomials passing through those points. So you need, even if you have D plus one many points, you need not be able to recover the secret correctly. So A is false. What about B? The correctness holds if the Lagrange interpolation is performed over integers. And integers are rings. And like, so you, so option A would create a problem. And one more problem that can happen is that you might not even be able, so you might not be able to even invert numbers, invert integers, right? For example, while trying to perform the Lagrange interpolation, you might need to divide by a few numbers. You might not be able to do that over integers. You might have to go over to rational numbers. So B is also false. What about option C? The privacy does not hold if the secret is said to be any term other than the constant term. This is also false. Even though in the Shamir secret sharing that we saw in the class used the constant term as a secret, it is not necessary that your constant term is the secret. You can also set some other terms to be the secret, as long as like as long as the so the dealer sets some term to be the secret, right? It is fine. It is fine if that term is something other than the constant term, as long as all the parties know which term has been set as the secret, and uh, as long as a polynomial picked by the dealer is random, provided that random conditions on the fact that secret is the secret is that term. Yeah. So like similar to a summary secret sharing scheme, we can create a similar scheme where the secret is some other coefficient. Yeah. So this is not a problem. So C is also false. And so yeah, none of these are true. Is this fine? Yeah. Now let's move on to the next problem. So the next two problems are about additive secret sharing and semi secret sharing respectively. So uh, the ninth problem is which of the following is or are true for the additive secret sharing scheme that we saw in the class? Option A is the shares of up to n minus 1 parties need not be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key between the dealer and every shareholder. Option B is regardless of the setup, the shares of all parties need to be communicated even if the adversary is computationally bounded. Option C is no shares need to be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key between the dealer and every shareholder. And option D is none of the above. So would you like to guess which of these is correct? Okay, you are saying B is correct. Actually, B is false. A is correct. And yeah, C and D are also false. Yeah, so A is correct. So let's see why A is correct. Yeah, okay, so yeah, the two things that may make A correct are this. Adversary is computationally bounded and there is this pre-shared random and private PRF key. So let's see why A is correct. So suppose shares with parties are K1 to Kn. Let the secret be yes. So here's what the dealer does. S1 to rather let it like this. Computes Si for all I n as Si equals to so F is the PRF. So the option A there was this secret random PRF key between the dealer and the shareholders, right? I'm calling the PRF F. So the PRF is F. Uh, so here is how it computes the shares or not n minus. So here is how the dealer computes the shares S1 to Sn minus 1. Now, using these S and S, it's supposed to compute Si, right? It then computes uh, Sn as S XORed with S1 to Sn minus 1. It shares Sn with Pn. Okay, so far the dealer has only shared one. Oh, I lost network. Yeah, I lost network for a while. Can you hear me now? Am I audible? Okay, yeah. Yeah, so the dealer computes S1 to Sn minus 1 and Sn. But instead of, so recall it in the Shamir secret scale sharing scheme, it was sharing S1 to Sn with P1 to Pn, right? Now what it's going to do is just going to share Sn to Pn. So it has just communicated one share to one party. So what about P1 to Pn? For all I in n minus 1, the party Pi can locally compute Si equals to Fki of I. Why? Because it has Ki, right? So P only needs to the share of one party to, yeah. So in the scheme that we have constructed so far, the dealer only has to share the secret share of one party to it, right? The nth party. The question is this scheme secure? Okay, so far we have only used one assumption that the dealer and the parties have a secret key between them, right? Have secret keys among themselves. What we haven't used is that A is computationally bounded. Okay, so security of the scheme. The adversary is computationally bounded. Okay, so if okay, let me call the adversary A. So now there are two cases, right? A controls so A can control up to n minus one parties. Uh, A controls P1 to Pn. Well, S1 to oh sorry, A controls P1 to Pn minus 1. So if A controls P1 to Pn minus 1, it has S1 to Sn minus 1, but these are independent. Uh, S. So A knows nothing about X. Similarly, case 2 is A controls N minus 1 parties, including Sm, sorry, Pm, without loss of generality. A controls P to T. Okay, so since A is computationally bounded, it cannot distinguish uh, S1 equals to Fk1 of 1 from a totally random string. So as far as A is concerned, S is indistinguishable. But let me get this. So if as far as A is concerned, uh, Shamir secrets the editor secret sharing scheme. Yeah, so since A cannot distinguish between the share of P1 and a completely random string, as far as A is concerned, that share might as well be a completely random string, right? But in that case, the additive figure, as far as A is concerned, the original additive secret sharing scheme was implemented as it is, right? And we know that that scheme is secure. Yeah, so in either case, A cannot know anything about us. So this secret sharing scheme in which we sent only one person share to it is also secure. So is this fine? Okay, so this means that A is correct. What about B? Regardless of the setup, the shares of all parties need to be communicated, even if the adversary is computationally bounded. Well, this is false because there is at least one setup where we only need to communicate one share, right? The setup in option A, that is when every party shares a random and private PRF key with the dealer, right? So option B is also false. Sorry, option B is false. What about option C? No shares need to be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key between the dealer and every shareholder. So what option C is saying is, in option A, we saw that just one share needs to be communicated. The question is, can we even get rid of that communication? So can we have a scheme which is completely non-interactive? Well, that is false. The reason is the following. if we do not communicate any of the S1 to Sn, then all of them are independent of S. So even if all parties come together, they still cannot compute S. In this case, the scheme won't satisfy correctness. Yeah. So we need to communicate at least one share with one of the parties. So C is also false. And D is false because A is true. So is this fine? Yeah, because if you have any question, ask now because this next problem is similar. Because if this is fine, let's move to the next problem. Okay. So the next problem is similar but for Shamir-Secret sharing. So which of the following is or are true for Shamir-Secret sharing? Option A is the shares of up to T minus 1 parties need not be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key between the dealer and every shareholder. Option B is regardless of the setup, the shares of all parties need to be communicated even if the adversary is computationally bounded. Option C is no shares need to be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key every dealer and between the dealer and every shareholder. And option D is none of the above. So depending on what we saw in the previous question, would you like to guess which options are correct over here? Okay, so just like in the previous question, so here also option A is correct. That is, if we have this special setup, then we can get away with not sharing the shares of up to T minus 1 parties. Let's see why. Dealer shares with uh, parties. Okay, again, let me call the dealer D. Shares with the parties P1 to PN, P K1 to KN, and let the secret VS. Now recall that in the Samir secret sharing scheme, the dealer is supposed to pick a random polynomial whose constant term is s, right? So in this case, also the dealer would pick a polynomial, but it it won't be completely random. It would be picked as follows. The dealer picks the polynomial, or rather, let me write the polynomial p. Okay, the polynomial. Okay, let me write it like this. Picks a polynomial of degree t such that a polynomial p of degree t such that its constant term is s, that is p of 0 is equal to s, i.e. p's constant term is s, and for all I in uh, t. So wait, this should be t. Yeah. So for all I in t, uh, p of I equals to f ki of I. Uh, in fact, so p is a degree t polynomial, and we have fixed its value at 1 and t points, right? So we have fixed its value at t plus 1 points. So in fact, p is unique since its degree is t and we have its evaluations t plus 1 points. Okay, so this is how it picks a polynomial p. Now remember that in the secret sharing scheme, it's supposed to evaluate this polynomial and then share the evaluations with uh, the parties, right? So it then computes Si is equal to f ki of I is equal to p of I for all I in t, and Si is equal to p of I for all I in uh, t plus 1 to n shares uh, s t plus 1 to Sn with parties p1 to p, sorry, pt plus 1 to pt. Yeah. So it only shares some shares with parties t plus 1 to tn. So it does not share shares with t parties p1 to pt. And what do p1 to pt do? Like how do they get their shares? Okay, so SI is P of I, but P of I is by definition by the way we have picked P, F, K, I of I, and each and every SI knows F, it knows I, and it knows Ki, right? So each and every PI can compute SI locally. So the dealer only had to share N minus 1 shares, and it did not have to share T shares, right? So this satisfies the condition in option A. The shares of up to T parties need not be communicated. But we also need to show that this scheme is secure, right? And again, the proof would rely on the fact that A is computationally bounded, and yeah, so it can't distinguish between random and pseudo-random strings. So A is computationally bounded. And so cannot distinguish Fk1 of 1 to Fkt of t from totally random strings. Strings or numbers. So these would be strings, but you can easily convert them to number by thinking of them as like numbers written in binary, right? So, uh, as far as A is concerned, or rather, let me A cannot distinguish between the pseudo-random polynomial at P of 0 is equal to S, P of I is equal to Fki of I for all I in T, and a random polynomial P prime whose constant term is 1. S since P of P prime I, sorry, P prime of 0 is equal to S, P prime I is equal to Ri for the random string Ri or random number Ri. So since A is computationally bounded, it cannot distinguish between P and P prime. So basically P is a pseudo-random polynomial, and what we have essentially done is we have implemented the Shamir-Secret sharing scheme with a pseudo-random polynomial instead of a completely random polynomial. The thing is, since A is computationally bounded, it cannot distinguish between the two, right? So as far as A is concerned, the original secret sharing scheme has been implemented. So since The original scheme is secure. So is the modified scheme against a computational bound. Yeah. So even this scheme is secure against a computationally bounded universe. Is this fine? So this proves that A is correct. What about B? Regardless of the setup, the shares of all parties need to be communicated, even if the adversary is completely bounded. Well, this is false because there is a setup in option A where you don't need to communicate all shares. You just need to communicate n minus 3 shares. What about option C? No shares need to be communicated if the adversary is computationally bounded and there is a pre-shared random and private PRF key between the dealer and every shareholder. Well, this is also false because again it would boil down to correctness. So C is false. If no shares shared by the dealer, then S1 to Sn are independent of the secret S. So even if any P parties come together, they still can't recover S. So the scheme won't satisfy. Yeah. So we do need to share at least some shares with the parties. So C is false. What about D? Well, D is false because A is true. Yeah. So again, over here the answer is A. We only need to share up at most like n minus T shares with different parties. Is this fine? Okay. So this is fine. Let's move on to the next problem. Okay. So next problem is again about additive secret sharing. So consider the following variant of the additive secret sharing scheme for sharing end-bit secrets among shareholders P1 to Pn. Oh, I should write skip P1 to Pn. Yeah. Now consider the following variant of the additive secret sharing scheme for sharing n-bit secrets among shareholders P1 to Pn, where up to n minus 1 parties can be corrupt. To share S, a string whose bits are S1 to Sn, the dealer gives Si to Pi. And the options are the scheme provides perfect security. The scheme provides computational security. The scheme is secure provided n is large enough, and none of the above. Which of these is correct? Okay, so the answer is none of these is none of the above. Uh, yeah. The answer is none of the above, and the reason is the following. Uh, so in the additive secret sharing scheme or in any secret sharing scheme, if n minus one parties come together, they should not know anything about the secret S, right? But suppose that over here n minus one parties, P1 to Pn minus one come together, then what can they find out about S? Well, Pi has Si. So P1 to Pn minus one together know S1 to Sn minus one, right? That is, they know S almost completely. All they do not know about S is the last bit of S, right? So in fact, not only is the scheme not secure, it's terribly bad because yeah, n, any n minus one parties that can come together and figure out S except just one bit of S. Yeah. So this scheme is not secure at all. So the correct option is B. Now let's look at the next problem. The next problem is for which of the following options are correct for the additive secret sharing scheme? Option A is the operations have to be performed over a ring. Option B is the operations have to be performed over a field. Option C is the scheme is secure even against computationally unbounded adversaries. And option D is the scheme is only secure against computationally bounded adversaries. So which of these is correct? Okay, so I don't have enough space. Let me move this. This much space should be fine. Yes, okay, yeah. Okay, so let's go over all the options. Option A is the operations have to be performed over a ring. In fact, this is false. We can even perform operations over a group. So let's see why. Uh, so let me call that group G. And yeah, since this is additive secret sharing scheme, I'll use the additive group. But yeah, you can also do the same thing with the multiplicative group. Okay, so the dealer picks S1 to Sn minus 1 uniformly at random from the group. So in the additive secret sharing scheme that we saw in class, the domain was strings. So we were randomly picking elements from, we are randomly picking strings. Now the domain is the group, so we'll randomly pick groups, sorry, elements from the group. So it would pick S1 to Sn randomly from the group and sets Sn to be S plus minus uh, S1, or rather, let me write like this. And where is the additive noise of SI range? Yeah, so this is what we can do in the additive secret sharing scheme, and The shared Sn would also be random because S1 to Sn are random. So basically the exact same arguments that we saw in the class for the correctness and the security of the additive secret scheme would also work over here. So we don't need to do operations over a ring. We can perform operations over a group as well. So A is false. What about B? The operations have to be performed over a field. Well, we don't need a field. We don't even need a ring. We just need a group. So B is also false. The scheme is secure even against computationally unbounded adversaries. This is true. We saw this in class, and the reason is, yeah, S1 to Sn minus 1 are completely random. So regardless of like which n minus 1 parties the adversary controls, S is still completely random for it. So the scheme is secure even against computationally unbounded adversaries. And option D is the scheme is only secure against computationally bounded adversaries. And that is false because C is true. Yeah, so the only correct option is C. This is fine. Okay, so let's move on to the next problem. So the next couple of problems would tell us like tell us of a very clear difference between MAC and digital signatures. So recall that both MAC and digital signatures are used to authenticate messages. As both are used to convince the receiver, the message came from a valid sender, right? However, there's a difference between the two, and these two problems would clearly illustrate this difference. So the first problem is about MAC. So there is a server A that wants to broadcast messages to end clients B1 to BN. Each client must be able to verify that the message was sent by A. For this, A uses MAC. What it does is the following. It shares the secret key K with all clients, and with every message, it appends a tag computed using K. The question is, if the MAC is secure, is the scheme secure? Is the scheme secure or not? Okay, so this scheme is not secure. So suppose that B1 wants to broadcast a message to all other clients, pretending to be N. Since okay, broadcast a message N to all other clients, and since it has K, it can compute a valid tag T for N and broadcast. All B2 to BN will think that the message came from me because it has a valid tag. Yeah, so B1 can impersonate A, and the solution for this would be the following. A shares key KI with BI for all I in N, and to send message out, it computes tags T1 to Tn, send keys K1 to Kn, and broadcasts M, T1 to Tn. BI accepts the message only if TI is a valid tag for M U with key K. Yeah, and so what A would have to do is it would have to share one key with all the all one like different keys with all the different parties. So it would have to share n keys, and not only that, it would have to broadcast a very big message, one message with the n tags to the parties. Now this key is secure because, well, since the party B1 does not have key K1, sorry, does not have any key from K2 to Kn, it cannot compute tags T2 to Tn. So to make this scheme secure, we need n many keys. Okay. Now what we'll see is in the exact same situation, if we use digital signature, we just need one key. So the next problem is there is a server A. It's the exact same situation, but now we use digital signatures. So there is a server A that wants to broadcast messages to n clients P1 to Bn. Each client must be able to verify that the message was sent by A. For this, A now uses a digital signature. It shares the verification key VK with all the clients, and with each message appends the signature sigma computed using the secret key SK. The digital signature scheme is secure. Is this scheme secure or not? Well, the answer is yes, because when compute a valid message, a signature pair, by just looking at without having the secret key. Yeah, so this is exactly what it means to say that a digital signature scheme is secure, right? Just because you have just because you have the verification key and have looked at a few messages, you shouldn't be able to forge a message signature pair, right? Without having the signing key S key. So this scheme is secure because whenever a party gets a message and it's signed by A, the party knows that it has to come from A because no other party could have forged its signature. So if we replace MAC by digital signatures, we just need one key which can be shared with all n parties. And the message that A needs to broadcast is also small, m comma sigma, just a message signature pair. Yeah. So this is like a very clear difference between MACs and digital signatures. Is this fine? Okay, so let's look at the next problem. The next problem is choose the correct option or options for SSL/DSL. Option A is it has two main phases. Option B is the handshake phase uses both public and private key primitives. Option C is the handshake phase uses only public key primitives. And option D is the record phase uses both public and private key primitives. So now let's go over all the options. Option A is it has two main phases. Well, that is true. And the main phases are the handshake phase and the record phase. Option B is the handshake phase uses both public and private key primitives. Well, this is also true because if you recall, uh, in the handshake phase, it uses public key encryption to establish secret keys that will be used in the record phase, as well as it uses at one place both the sender, sorry, or both the server and the client use MAC to authenticate some messages, right? Authenticate some transcripts. So now, like public key encryption is obviously a public key primitive, and MAC is a private key primitive. So both public key primitives and private key primitives are used in the handshake phase. Option C is the handshake phase uses only public key primitives. That is false because it also uses private key primitives, in particular MAC. And option D is the record phase uses both public and private key primitives. This is also false. And in the record phase, we just use private key primitives. In particular, we just use key encryption and MAC to send authenticated, like to send messages using an authenticated encryption scheme. And the reason that we don't use public key primitives in the record phase is the following. Now, the handshake phase only happens once, right? At the very beginning of the communication. So there are only a few messages sent in the handshake phase, and it is fine if we use some heavy public key primitives over there. It is fine if okay, the public key primitives require much more computation, right? They are much less efficient than private key primitives. So it's perfectly fine if we use some heavy computation for the handshake phase because it only happens once. On the other hand, once the handshake has been established, there would be a communication that there would be lots of messages sent between the sender and the receiver or the server and the client in the record phase, right? Because in the record phase would be too inefficient. Since a lot of messages are sent, we only want to spend like a very small amount of time to send every message, and so we use private key primitives for the record phase. So only option A and B are correct. So now let's look at problem 16. So this problem is suppose that we use a t plus 1 comma t additive secret sharing scheme to share an m-bit secret across n parties such that no set of up to t plus 1 parties can recover the secret. That is, we want to do n comma t secret sharing for m-bit messages, but using t plus 1 comma t additive secret sharing schemes. Then how many total shares does the dealer have to share? How many bits must the dealer How many shares will a single party possess? How many bits must the and how many bits must the dealer share with each party? So let me add an extra. Yeah. So recall that for every S subset of n of size t, the dealer shares secret shares probability this. The dealer uses separate t plus 1 comma t secret sharing, or rather separate instance of the t plus 1 comma t secret sharing scheme for parties. Uh, Pi, so the number of shares is equal to number of subsets S of n, such that size of S equals, oh wait, size of S equals t plus 1 times the number of shares shared in one instance. Secret sharing. Okay, so the number of subsets of S of n of size t plus 1 are exactly n choose t plus 1. And the number of shares shared in one instance of a t plus 1 secret sharing scheme. Well, what is that? That is, so with in the t plus 1 comma t secret sharing scheme, there are t plus 1 parties and the dealer shares one share with each of them, right? So this number is t plus 1. And this is exponential if t is large, right? The second was number of bits. So this is just number of shares times bits per share. Now, we know this number, we just computed it. 10 choose t plus 1 times t plus 1. And how many bits are there per share? Well, we want to do secret sharing for m bit secrets. So each and every share would have sizes of these many bits per party. Okay, so the number of shares that one party would possess. Okay, so what happens? Suppose if a party I, uh, it wo- it would engage in the secret. It would engage with all combinations of t other parties in secret sharing, right? So the number of shares per party is equal to the number of subsets S of n such that size of S equals t plus 1 containing say party I times number of shares uh, ith particles in one instance of t plus 1, comma t squared. Now, how many subsets of size t plus 1 are there which contain I? Well, I is already in the set, so we are left with n minus 1 elements from which we can pick t elements, so it's this. And how many share does one party get in one instance of t plus 1 comma t secret sharing? Well, it just shares. And number of bits uh, a dealer has to communicate to the ith party. So this is exactly equals to the number of shares ith party possesses times bits per share. Okay, so we just computed the number of shares the ith party possesses n minus 1 times t, and bits per share is n, so these many bits. So yeah, not only does the dealer have to send out a lot of shares and a lot of bits, each and every party must also store a lot of shares and a lot of bits. So this scheme is very inefficient. Yes, so we are out of time. So yeah, let's meet for the last problem solving session next Saturday from 4 to 6. Thank you.